Pluto, a distant and enigmatic dwarf planet that was once part of our solar system's planetary family, has been the subject of renewed attention due. According to observations, Pluto's trajectory is alarmingly close to that of Neptune, which has led astrophysicists to warn of the possibility of a future collision between the two celestial bodies, posing a potential threat to Earth. The uniqueness of Pluto's journey around the Sun lies in its unusual orbit, requiring an extraordinary 248 years to complete a full cycle. Since its discovery in 1930, Pluto has yet to complete a single full orbit. The intrigue intensifies when considering the highly elliptical shape of Pluto's orbit, which differs significantly from the nearly circular orbits of the larger planets. The remarkable inclination of Pluto adds another element of peculiarity. Compared to the rest of the planets in the solar system, with an inclination angle of 17 degrees with respect to the plane of the ecliptic, Pluto's orbit is markedly different from the trajectories of the other planets. The combination of this steep inclination and its elliptical path contributes to the complexity of its orbital pattern. One of the most fascinating elements of Pluto's orbit is its intersection with the trajectory of Neptune. For approximately 20 years in each orbit, Pluto comes closer to the Sun than Neptune, defying conventional expectations about their relative locations in the solar system. The answer lies in the gravitational influences of other planets. Research on Pluto's orbit began soon after its discovery. Initially, astronomers struggled to understand the uniqueness of its trajectory. Unlike the other planets, which orbit close to the plane of the ecliptic, Pluto's path is both inclined and elliptical. The intrigue grew with the realization that Pluto's orbit crosses that of Neptune. The stability of Pluto's orbit, despite its complexities, serves as a testament to the intricate laws governing celestial mechanics. The three-body problem in space refers to the challenge of understanding how three celestial objects, such as Pluto, Neptune, and the Sun, move and affect each other through gravity. It involves predicting their trajectories based on their initial positions and mutual gravitational interactions. In Pluto's case, this problem reveals complex interactions among its trajectory, Neptune's path, and the Sun's gravitational pull. Recent computational analyses have shed light on how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit. There exists a special resonance between Neptune and Pluto. For every 2 complete revolutions Pluto makes around the Sun, Neptune makes 3. This orbital resonance plays a crucial role in maintaining stability in Pluto's trajectory. However, Neptune is not alone in this dynamic. Jupiter's gravity also plays a significant role in stabilizing Pluto's orbit, and Saturn contributes in a more modest way. Evidence suggests that Jupiter's gravitational influence alone is powerful enough to ensure the long-term stability of Pluto's orbit, even over billions of years. Collectively, Neptune, Jupiter, and Saturn act in concert to maintain Pluto's relatively smooth motion through space. These gravitational phenomena are crucial for maintaining order and predictability in the solar system. Without such mechanisms, the system would be far more chaotic, with increased risks of collisions and orbital disruptions that could trigger a domino effect among celestial objects. In Pluto's case, especially when contemplating the potential for future interactions with Neptune, a detailed understanding of its orbit is essential. This provides clearer insight into the dynamics of the solar system and demonstrates how even seemingly unstable orbits can reach equilibrium through the interplay of gravitational forces and orbital laws. It also underscores the continued importance of astronomical observation and study in understanding our place in the cosmos. The exploration of deep space often reveals the unpredictable nature of celestial bodies, and Pluto's orbit is a prime example of orbital chaos. This concept refers to the extreme sensitivity of a celestial body's trajectory to its initial conditions, a phenomenon clearly seen in Pluto's motion. Even minor changes in Pluto's characteristics can significantly impact its long-term orbit. Computer simulations have been a valuable tool for scientists exploring Pluto's behavior. These simulations use complex equations to model gravitational interactions between Pluto and other celestial objects like Neptune. By adjusting initial conditions, astronomers can observe how even slight variations can cause significant changes in Pluto's trajectory. In the 1980s, such simulations revealed intriguing aspects of Pluto's motion. Although stable in certain parameters, its orbit can become chaotic and unpredictable if it begins with slight differences in position or velocity. Over time, these differences can lead to drastically different outcomes. Yet, despite this potential for chaos, Pluto's orbit has remained stable over billions of years, suggesting an underlying order within the apparent randomness. Predicting cosmic events, especially those involving chaotic orbits like Pluto's, remains a significant challenge. The inherent unpredictability of these systems means that long-term projections are often uncertain. Although numerical simulations are powerful tools for understanding the future trajectories of celestial bodies, they also highlight the limitations of our predictive capabilities. These models rely heavily on accurate initial conditions and complete understanding of gravitational interactions. Small errors or oversimplifications can produce vastly different outcomes. Additionally, the chaotic nature of certain orbits, such as Pluto's, reminds us that the universe is dynamic and continuously evolving. While our understanding of space has advanced considerably, Pluto's case reveals that much remains unknown. It highlights the importance of ongoing research and observation in refining our models of the cosmos. Pluto's orbit also opens the door to a deeper philosophical question about how we define stability in a cosmic context. While its orbit is technically stable over long time scales due to gravitational resonances, its sensitivity to initial conditions and interactions with larger planetary bodies means that this stability is always on the edge of chaos. In this way, Pluto becomes a case study in the broader field of dynamical systems and chaos theory, disciplines that seek to understand how complex systems behave over time. Furthermore, Pluto challenges our planetary classification system. Its demotion from planet to dwarf planet by the International Astronomical Union in 2006 sparked intense debate. Critics of the reclassification argued that Pluto's unique features, its atmosphere, moons, and complex orbital dynamics, deserve recognition on par with other planets. Supporters of the change pointed out that Pluto fails to clear its neighborhood of other celestial objects, a key criterion for full planetary status. This ongoing debate reflects the evolving nature of scientific understanding. As our tools for observation improve and our theoretical frameworks expand, definitions once thought to be fixed can change. Pluto, with its mysterious orbit and peculiar status, represents this transformation well. It stands as a symbol of how new data can upend old models and how even distant icy worlds can reshape our cosmic worldview.